Paper 2 from May 21, Timezone 2. Starting off with what seems to be a limestone cycle, where calcium carbonate can be converted into calcium oxide, oxide to calcium hydroxide. We're going to start off with the first step, calcium carbonate turning into calcium oxide and carbon dioxide via decomposition. We're given a mass of calcium carbonate to start off with, and this will convert to a specific amount of carbon dioxide, and we are asked to calculate that. We're asked to calculate the amount of calcium carbon dioxide produced and the corresponding volume of carbon dioxide produced. How do we go about this question? We first calculate the amount of calcium carbonate in moles. How do we do that? We do N equals M over big M, where mass is 555 grams over the molecular mass of calcium carbonate, which, if we do the calculation, would be, specifically speaking, 100.09 grams per mole. Okay. Do the math, will be given 5.55 mole. What do we know about the amount of carbon dioxide produced then? It will be equally 5.55 mole. Why? Because 1:1 molar ratio of carbon dioxide, calcium carbonate to carbon dioxide, which means that the amount of carbon dioxide will also equal to its volume over 22.7 dm cube per mole, which means if we multiply 5.55 mole by 22.7, we will be given the volume of carbon dioxide in mole. So let's do the math now. Volume of carbon dioxide will equal to 5.55 times 22.7, which in turn would be 126 dm cube. Next up, we're going to calculate some enthalpy change. We're given the enthalpy change of formation values, for which we're going to set up the Hess cycle. Since we are dealing with delta HF, we're going to utilize how the constituent elements of the reactants and the products in our equation, which are carbon solid, calcium solid, and oxygen gas, will be forming calcium carbonate with minus 1207 kilojoules per mole, calcium oxide minus 635, carbon dioxide with minus 393.5. The math we have to do is to work out our delta H. To work out our delta H, set up the equation that delta H would equal to minus 1207 plus minus 635 plus minus 393.5, which would equal, in turn, plus 127 kilojoules. We are now asked to draw the energy profile for a catalyzed reaction. What's the difference between a catalyzed and uncatalyzed? Well, it's going to be the difference in the magnitude of activation energy. In other words, the height between the dotted line of transition state. We are going to label the dotted top line as the transition state, and the energy level of our reactants is what we define as the activation energy. We are going to reach the transition state of the catalyzed reaction at a lower energy value. And what that leads to is a lower activation energy. The EA of catalyzed is lower than that of the uncatalyzed. So we will need to draw the diagram so that the curve peaks lower, like we have drawn. And why does this happen? How does catalyst lead to such effect? Well, the question is asking, why does the activation energy decrease? And that's because catalysts provide an alternate reaction pathway. Alternate reaction pathway. We're now going to move to the second step of the limestone cycle, where calcium hydroxide is produced. And calcium hydroxide would react with hydrochloric acid to produce something. Write the equation for the reaction of calcium hydroxide with hydrochloric acid. Well, it's going to be base, calcium hydroxide, specifically alkaline, because it's soluble base, reacting with our acid. So acid-base reaction, neutralization reaction. Therefore, that something is going to be a salt and water. Let's show that with calcium hydroxide plus HCl. Let's make sure we acknowledge the state of the reactants as both aqueous, turning into our salt, calcium chloride. But calcium chloride is a 2+ cation meeting -1 halide, anion. Therefore, we will need 1:2 ratio of our metal and non-metal. CaCl2 plus H2O means we're going to have to touch up on the stoichiometry of this equation. So, in order to produce CaCl2, we will need to add in 2HCl. And if we do add in 2HCl, that means we'll produce 2 water. 1 CaOH2 with 2HCl will produce 1 CaCl2 and 2 H2O. Correctly calculated. Just going to add the state symbols of our products. Calcium chloride will be a soluble salt, therefore aqueous, while water in its natural state will always be liquid. We are asked to do some titration question for neutralization reaction. So we're given the volume and the concentration of HCl and only the concentration of calcium hydroxide, because we'll work out its volume. Okay. So for titration of neutralization reaction, always draw a table. A table where we have our calcium hydroxide on the left column and HCl on the right column. We're going to have 3 rows. The first row being the amount in mole, which we don't know yet. We'll have to calculate these values. The second row is going to be the concentration in mole per dm cube, or big M. The third column is going to be volume in dm cube. Now, some of these empty boxes we can already fill in, like the concentration value of calcium hydroxide. 0.015 is what we know. We don't know the volume. We don't know the amount as of now. But we can by filling in the concentration value for HCl as 0.025, the volume 35 cm cube. But we do want the volume to be in dm cube, therefore 0.035 dm cube. From here, we can work out the amount of HCl present. How? N equals CV. N equals CV is the amount calculation equation we use for liquid states. So N equals CV, we will be given 0.00088 mole. From here, we can work out the amount of calcium hydroxide that reacts with 0.00088 mol of HCl. How? Well, we know that calcium hydroxide reacts with HCl in 1:2 ratio. 1:2 ratio tells us that calcium hydroxide amount must be half of HCl's amount, meaning it will be 0.00044 mole of calcium hydroxide. From where we can work out the volume of calcium hydroxide. The volume of calcium hydroxide, VCaOH2, would be the amount over concentration. Do the math, and we will be given 0.029 dm cube. The answer being 0.029, we will have to put it out of the table and specifically mention this value to be 0.029. What's the unit? dm cube. Calcium hydroxide produced will have a pH. And we are asked to calculate the pH if the solution has a specific concentration. The concentration being 2.33 10 to minus 2. Okay. To calculate the pH, we will need H plus concentration. Or another way would be so we can work out the pH with the information of H plus concentration, or knowing the relationship between pH and pOH, where addition of pH and pOH will equal to 14. And this relationship is derived from the ionic product of water, which is represented as H plus times OH minus concentration equals 10 to minus 14 at room temperature. We're going to go for the second route, pH equals 14 minus pOH, because that's a bit easier. Going to work out pOH because we know calcium hydroxide will produce OH minus when dissolved in water. We call this dissociation. And how does calcium hydroxide dissociate? Well, calcium hydroxide would dissociate completely in water, which we can represent as calcium hydroxide turning into calcium 2 plus and 2OH minus. Calcium hydroxide aqueous, calcium 2 plus aqueous, hydroxide aqueous. If we start with 2.33 times 10 to minus 2 big M of calcium hydroxide, we will end up with 4.66 times 10 to minus 2 big M of hydroxide ion, which means that the pOH will be minus log OH minus, meaning minus log 4.66 times 10 to minus 2. Do the math, and we'll be given 0.029 1.332. Now, back to the question. To work out pH, we'll have to use pH equals 14 minus 1.332, meaning our answer would be 12.668. We're approaching the end of our limestone calcium carbonate cycle, where calcium hydroxide needs to turn back into calcium carbonate. And how does it do that? Well, we're now told that calcium hydroxide will react with carbon dioxide in the following 1-to-1 ratio: calcium hydroxide plus CO2, calcium carbonate with the byproduct water. Again, stoichiometric question. We need to find the mass of product formed, the product being calcium carbonate, if we are given the amount of calcium hydroxide. Okay. Actually, we are given the amount of both calcium hydroxide and carbon dioxide. And it appears that this question is about identifying which of calcium hydroxide or carbon dioxide is limiting or excess. And we'll have to consider the fact that there's a limiting reagent to find out the amount of product formed. Let us start by working out the respective amounts of both reactants. Okay. Initially, we're going to have 2.41 times 2.33 times 10 to minus 2. N equals CV. V being 2.41, C being 2.33 times 10 to minus 2. Now this, do the math, will give us the mole to be 0.0562 mol. Carbon dioxide will have the mole of 0.75 over 22.7. Using the equation, N equals volume over 22.7 for gas. Do the math, we will be given 0.033 mol. Comparing the two amounts, we can tell how calcium hydroxide is in excess. Calcium hydroxide amount is greater than the amount of carbon dioxide. Carbon dioxide is the limiting reagent, meaning that at the end of the reaction, we will have 0 mole of carbon dioxide. We will have 0.0232 mole of calcium hydroxide, and we'll have 0.033 mole of calcium carbonate, 0.033 mole of water. Our answer being 0.033 mole of calcium carbonate, we'll use N equals mass over molecular mass to work out the mass of calcium carbonate, our product. Mass is equal to amount 0.033 mole times the molecular mass of calcium carbonate, 100.09 grams per mole. Do the math, and we'll be given 3.30 grams. Okay. The technique that I like when doing stoichiometric question is to always write the initial amounts and the end amounts. Omitted that I'll input now is the initial amounts of our products, which you already should know should be 0 moles for both calcium carbonate and water. Okay. Unlike the 3.30 grams of calcium carbonate that we expected to produce, only 2.85 grams was produced, which means the percentage yield is not going to be 100, as it usually isn't. If we work out the percentage yield, we will work it out as percentage yield being the actual amount produced over theoretical, which means 2.85 grams over 3.30 grams. Do the math, and we'll be able to work out how we have 86.4% for the percentage yield. We had many calcium compounds, starting with calcium carbonate, calcium oxide, and calcium hydroxide. In fact, all of these 3 compounds should be able to aggravate the effect of acid deposition. Sulfuric acid, nitric acid produced from acid deposition should neutralize with either of all of calcium carbonate, calcium oxide, and calcium hydroxide. So we're going to add any of these 3 or all of these 3 to acidic water, acidic lake, acidic soil. Add calcium carbonate or calcium oxide or calcium hydroxide to the environments that are experiencing the effects of acid deposition, acidic water, lake, soil, and etc. The second question of this paper starts with the periodicity. Happens to be my favorite, and the first trend we're going to investigate is the generic decrease of atomic radius across the period. We're going to look at period 3 that has aluminium and silicon, comparing why silicon has a lower radius than aluminium. The third period has sodium, magnesium, aluminium, the metal we're looking at, and then the silicon. Sodium will have higher atomic radius than magnesium, in turn higher than aluminium and higher than silicon. Well, across the period, the number of protons increase, which means the nuclear charge increases, meaning the electrostatic attraction between the nucleus and the valence electrons gets stronger, resulting in atomic shrinkage. So, aluminium has greater atomic radius than silicon because aluminium has higher number of protons than silicon. This itself is 1 mark. And this is equal to saying how aluminium has greater nuclear charge. The second point will come from acknowledging how there is electrostatic attraction between the nucleus and the valence electron. And this electrostatic attraction increases. As a result, or leading to, so I got the subject of our question wrong. Aluminium does not have higher number. It's the silicon that has higher number. Silicon has higher number of protons than aluminium. Don't know why I wrote that. We're going to compare the size of a sodium atom and the sodium 1+ cation. We know sodium cation is going to be smaller than a sodium atom for two reasons, for which we're going to be given 2 marks. First is the obvious reason that sodium atom has 3 electron shells compared to the 2 electron shells of a sodium cation. So sodium has 1 more electron shell than sodium plus. The second reason is not so obvious, but it's to do with the electrostatic attraction between the nucleus and the valence electrons that leads to the shrinkage of the atom and the anion. We're going to pay attention to 2 key terms. That's shielding effect as well as the effective nuclear charge. How many protons are there in a sodium? We have 11. We have the mass number of 23 because we've got 11 protons and 12 neutrons. What about a sodium ion? We still have 11 protons and 23 protons and neutrons. It's just that we have 1 electron less. And what impact does this have on the electrostatic attraction? Well, we're going to pay attention to the term effective nuclear charge, where effective nuclear charge is given by the number of protons minus the number of non-valence electron shells, by the number of non-valence electrons. How many non-valence electrons are there in a sodium? Think about the electron configuration. The electron configuration of sodium is what? Is 1s2, 2s2, 2p6, and 3s1. We have 10 non-valence electrons that will be imposing the shielding effect. So 11 protons minus 10 non-valence electrons leads to 1 proton that is able to pull on that 1 valence electron. So we call the effective nuclear charge of sodium as what? +1. +1 is the effective nuclear charge of a sodium atom. But what about sodium ion? Well, sodium ion will now have electron configuration of 1s2, 2s2, and 2p6 only. And what does that mean? Well, the number of non-valence electrons has decreased, which means that the effective nuclear charge has increased. And therefore, the resultant electrostatic attraction between the nucleus and the valence electron of a sodium ion has increased, leading to further shrinkage. How do we write this in words? You want to say that effective nuclear charge of Na is, let's say Na plus, is greater than Na. Therefore, experiences stronger effective electrostatic attraction between nucleus and valence electrons, which leads to ionic shrinkage. Electron configuration, but condensed, which means we're going to skip the electron configuration of the first and second electron shells. Oh no, sorry, we're going to skip the third electron shell as well because we're dealing with transition metal, chromium. Chromium is where? Is in d block orbital, and it's the fourth transition metal after vanadium. So if you look at the first row of d block, it would be scandium, titanium, vanadium, and then chromium. Being the fourth one, we do expect the electron configuration to be 3d4 after having filled the 4s2 with Ar. Argon configuration will condense the preceding electron shells electrons. However, copper and chromium are the special transition metals where, in order to complete or half complete the 3d orbital, we're going to excite one of the 4s orbital to the 3d, so that we have 5 instead of 4. For copper, 10 instead of 9. Why? Because half filled or complete d orbitals are half complete, and complete d orbitals are more stable. Therefore, the chromium will have condensed electron configuration of Ar 4s2, no, sorry, not 4s2, 4s1 and 3d5. Then we have the chromium ion with the oxidation state as 3+, meaning we have lost 3 electrons from 4s1 and 3d5. Aufbau principle states what? It states that electrons occupy lowest energy orbitals first. That's why 4s orbital is occupied before 3d. So empty 4s orbital has lower energy than empty 3d. But remember, occupied 4s has higher energy than occupied 3d, meaning 4s electron or electrons will be removed first when undergoing ionization. So we will end up with Ar. Let's remove 4s1. Then let's remove 3d2, leaving us with 3d3. Metallic bonding is defined as the electrostatic attraction between what and what? Electrostatic attraction between a lattice of metal cations and surrounding sea of delocalized electrons. That's what the nature of metallic bonding is. What's special about the delocalized electrons? They can freely move across the lattice, meaning the movement of negatively charged electrons lead to production of electricity. free movement or unrestricted movement of delocalized electrons confer metals their electrical conductivity property, physical property of metals. Free movement of delocalized electrons is electrical conductivity. So yeah, SCl2 stands for what? Sulfur dichloride. Well, there's going to be two single covalent bonds between the sulfur and the two chlorines, which will be drawn as SCl, Cl. Sulfur has how many valence electrons? 6, out of which 2 have been used in bonding pairs, meaning the remaining 4 will be used in the 2 lone pairs as drawn there, right there. 4 electron domains, out of which there are 2 bonding pairs and 2 lone pairs. And what shape, what molecular shape do we refer to this? We refer to these as bent shape. Bent or V-shaped. We're going to compare the volatility of sulfur dichloride and water. Water has lower volatility than sulfur dichloride. In other words, water has higher boiling point because stronger intermolecular forces. Because of stronger intermolecular forces. And why does water have stronger intermolecular forces? Water has hydrogen bonding. While HCl does not. Both water and HCl has London dispersion forces, dipole-dipole moment, dipole-dipole interaction, but only water has hydrogen bonding, which is the strongest intermolecular forces of all the 3 intermolecular forces. Position of equilibrium is affected by multiple factors, which includes pressure, which is exactly what we're looking at in our question, where the stimulus increasing the volume directly leads to decrease in pressure. So we'll be looking at pressure, but besides pressure, there can also be temperature, concentration, and catalyst. Doesn't directly affect POE, position of equilibrium, but we deal with catalyst when it comes to position of equilibrium. So pressure, temperature, concentration, catalyst are the factors that affect POE. And what's the formula? The formula is that equilibrium system, always will counteract a change in any of these factors. We're going to be looking at the decrease in pressure, right? The system will counteract decrease in pressure. Decrease in pressure will be counteracted by favoring either the forward or the backward reaction. Favoring. In our case, we want to favor either the reactant or the product side, and whatever has higher moles will be favored. For example, in our equilibrium, the reactant side has more moles than the product side. Therefore, the reactant side will be favored. Reactant side with higher moles. And this will result in what? The position of equilibrium shifting to the reactant side. Okay, so we are going to, how do we put this into writing? We're going to put these into writing by saying that pressure decrease is counteracted by favoring the side with higher moles of, let's say, species. As a result, position of equilibrium shifts to the reactant side. We mentioned how there is pressure decrease, how there's the counteraction by favoring the side with higher moles, and therefore the POE shifting to the reactant side. That's how we get all the 3 full marks. Voltaic cell question for question 3, where we're comparing aluminium with tin. We are given a voltaic cell that are not labeled at all. So we're going to start labeling with the easy voltmeter. Salt bridge. A typical salt bridge is going to be potassium nitrate, and we want to use potassium nitrate in this case because the electrolytes of anode and cathode both contain nitrates, tin nitrate and aluminium nitrate. Electrons flow from the anode to the cathode, meaning on the left we have the anode, on the right we have the cathode. Aluminium has higher oxidation potential than tin, and we know that because looking at the activity series, aluminium at the relatively top of the list will have greater activity than tin, meaning it's more reactive, it remains oxidized, while tin 2+ will be reduced. So oxidation that takes place at the anode will have aluminium metal electrode, with the electrolyte being aluminium nitrate. The cathode will have the tin metal electrode, with the electrolyte being tin nitrate. The overall chemical reaction would be the simultaneous addition of the oxidation half equation and the reduction half equation. Let's write the oxidation of aluminium. Aluminium solid will oxidize to aluminium 3+ aqueous, releasing 3 electrons. Tin 2+ aqueous will gain 2 electrons to become tin solid. We want to add these 2 half equations. We'll have to utilize 6 electrons. We're going to use 6 electrons, meaning we will multiply the oxidation half equation by 2, and we'll multiply the reduction half equation by 3. So that overall we'll end up with 2Al solid plus 3 tin 2+ aqueous turning into 2Al3 plus aqueous and 310 solid, with the 6 electrons on left and right, reactant and product sides cancelled out. Organic chemistry for question 4, where we start with but2-ene, a symmetrical alkene that is undergoing electrophilic addition with 2 different electrophiles, starting from hydration, addition of water, with sulfuric acid as one of the conditions or reagents. And we will be ending up with an alcohol because H2O will be inserted into the but2-ene molecule instead at the sacrifice of the double bond. We'll break the double bond to insert H2O so that we end up with H3C, or let's just draw these out. We're going to have 4 carbons. And we're going to add our hydroxyl group, making the identity of our product an alcohol. We have buta-2O. Buta-2O is our product from hydration. But if we use hydrogen for our electrophile, for the process hydrogenation, we will be producing an alkane, a butane. This may be called hydrogenation or simply reduction, addition of hydrogen. We may combust but2-ene. We may combust an alkene, which means react with oxygen, just like we can combust alkanes. We'll be producing carbon dioxide and water, and the delta H we can expect to be a negative value for the combustion being exothermic process. But exactly what's the exact delta H? What's the exact enthalpy change? We can work this out via 2 routes: bond enthalpy calculation or delta H formation using Hess cycle. Section 11 tells us that we should use bond enthalpy. We should use bond enthalpy values. Let us start calculating the bond enthalpies of our products and reactants. Why? Because the bond enthalpies of products will be representing the energy released from formation of new bonds, while the enthalpies, the bond enthalpies of the reactants will be representing the energy required, the energy inputted to break the existing bonds. Which means the bond enthalpy values for products will be negative, and the bond enthalpy values for the reactants will be positive. So delta H will be the sum of the 2 bond enthalpies, meaning delta H equals sum of bonds broken minus sum of bonds formed. And this may be represented as bond enthalpies of reactants minus bond enthalpies products. Let's look at what the bond enthalpies of the reactants are. We are going to have, for bond enthalpies of reactants, quite a lot of bonds. We're going to have quite a lot of bonds. We have C-C double bond, one of it, and a C-C carbon single, and there are 2 of them. We also have CH, which would be 8. We have 8 CH single covalents. And that is it for the butene, but if we include oxygen double bond, we will have 6 of oxygen to oxygen double. Let's make sure that we have not left out any bonds for butene by actually drawing butene. 8 carbon to hydrogen singles, 1 carbon to carbon double, 2 carbon to carbon singles. We have not omitted any bonds. Now, if we derive the values for the 4 different bond types, we'll start off with carbon to carbon. Carbon to carbon, 614 kilojoules. Let's put this in a different color. 614 kilojoules. Carbon to carbon single. Carbon to carbon single is 346. 346 times 2. 346 times 2. Carbon to hydrogen. Where is carbon to hydrogen? Carbon to hydrogen is right here, 414. 414 times 8. Finally, oxygen to oxygen, 498. The sum of the 4 values would be our reactant bond enthalpies. Let's look at the bond enthalpies of our products. We'll use a different color. We do have, for carbon dioxide, carbon to oxygen double, and there will be 8 of it. Why? Because we've got 4 carbon dioxides, and per carbon dioxide, there are 2 of carbon to oxygen doubles. We have O to H, and we have, again, 8 of these. 4 water, where each water has 2 OHs. 804, while OH has 463. 804 times 8, 463 times 8 would give us the product bond enthalpy value. Let's do the math, and we will end up with the delta H becoming, let's use a different color. The answer would be minus 2530 kilojoules. When an alcohol meets a carboxylic acid, in our case, ethanol, let me draw ethanol. I'm going to draw ethanol inverted. Here is our ethanol and a carboxylic acid. In our case, methanoic acid. How do we draw a methanoic acid? Well, let's draw the carboxylic group, COOH, first, and then another final H. What we know is that when the two react, there's going to be a condensation reaction. And where does the condensation reaction come from? Well, I'm going to slightly modify the drawing we have to have the OH that belongs to the ethanol drawn as O covalent bond H. The condensation occurs from the OH of carboxylic group and the H of the alcohol OH condensing out, so that the oxygen, remaining oxygen, bonds to the originally carboxylic group's carbon. And as a result, we're going to form a new homologous series, a new functional group called the ester. And if I draw the ester, we're going to have a new molecule called ethyl methanoate. The alcohol part will always turn into the alkyl, let's say the side group, alkyl, in this case ethyl, and the carboxylic acid will turn into carboxylate, methanoate. In terms of the equation, you want to write HCOOH plus C2H5OH turning into HCOOC2H5. And is this the end? No. If you left out the byproduct of this esterification reaction, you would not get the mark. This is called what? A condensation reaction. And therefore, it's indispensable that you put in water. And the product name? Ethyl methanoate. Okay. A bit of a further practice would be, what if we had a methanol and a ethanoic acid reacting together? Then it would be called the methanol turning into methyl, ethanoic acid turning into an ethanoate. So methyl ethanoate. Just in case we come across more questions in future. Yes, an alcohol like ethanol, being a primary alcohol, can be oxidized and further oxidized into an aldehyde as well as a carboxylic acid. In our case, ethanol will be produced by a simple distillation where there will be ethanol with the lower boiling point vaporizing, leaving the distillation flask as vapor, which we can collect. Ethanol can be collected via distillation. And if we picture what distillation looks like, it would simply be having our ethanol boiled with heat, where we will be having the vapor leaving the flask as ethanol. But if we want to produce ethanoic acid, we need the ethanol back into the flask so that it keeps being further oxidized. And how do we achieve this? We put a cooling jacket. We put a cooling jacket around the flask. Cooling jacket around the flask so that the leaving vapor returns back and continues to get boiled and continues to get further oxidized. We call this distillation under reflux. Distillation under reflux. And this will produce ethanoic acid. And what's ethanoic acid? Ethanoic acid has quite a high boiling point, certainly higher than ethanol, and will be in the form of liquid, remaining in the flask. We're going to look at a new compound, a new organic compound, for which we do not know its chemical formula, but we are given some spectroscopy data, starting with mass spectroscopy. Let's look at the mass spec data, where we do have two distinct peaks at 58 mass to charge and 43. Okay. Now, what are the features? Or what are the 58 and 43 peaks? Well, we do know that the compound on the question is a hydrocarbon with oxygen, CHO, and the molecular mass of our compound, 58 grams per mole. Why? Because the highest highest mass to charge ratio of highest mass to charge value is 58, which means that, and that peak corresponds to the unfragmented molecule, so the molecular mass must be 58 grams per mole. Another high peak at 43 means that it's a fragment that has lost a mass to charge unit of 15, which corresponds to CH3. So there are CH3 fragments that can be easily lost from our compound. So CH3 lost. We are then given further information about the type of groups present on this unknown compound by with this IR data. Infrared data, especially with the peak at A, which correspond to 1700 cm-1. According to the infrared data, we can tell we are specifically looking at carbonyls. There is a carbonyl. There's a carbonyl group within our unknown compound. We're now given some NMR data which shows a single peak spectrum, which means there's only one hydrogen environment. And that tells us a lot about what our molecule is. What can we deduce from this information? Well, it's a single peak, tells us one single peak spectrum means only one hydrogen environment. And this hydrogen environment has a specific chemical shift value, 2.2. And if we look at the NMR data, 2.2 containing NMR data tells us this molecule could either be a CH2 bonded to a CH2 within an ester, or a CH2 within a ketone. Okay, could be either. But because we know that there's a carbonyl group, not an ester group, we know ketone will be the homologous series of our unknown compound. So we know that our molecule will be single peak means only one hydrogen environment, and this hydrogen environment is next to a carbonyl, which means the compound we can elucidate is a symmetrical compound. Must be symmetrical so that there's only one hydrogen environment. And it could be a propanol or a pentanol, specifically pentathione. So let's potentially think of propanol and a pentanol, but specifically pentathione. We do have some mass spec data that our unknown compound has 58 grams per mole. So if we work out the MR, the relative molecular mass of propanol and pentathione, we'll be able to decide either of which. Propanol CH3CO CH3 has 12.01 times 3 plus 1.01 times 6 plus 16. 36, 52. Okay. Our answer is propanol because the MR of propanone is 58. So the compound is propanol. We have used mass spec data, IR data, and NMR data to work out what an unknown compound is, what the identity of the unknown compound is.